Dear colleagues, I will present the C3D kernel capabilities for the direct modeling operations. First of all, I would like to briefly describe what direct modeling is about. It works directly with faces of a solid and doesn't require a build lock. Its main usage is to work with solids that doesn't have build lock, for example, because of import. Also, it can be used to perform small final changes in place. C3D geometric kernel capabilities are listed on this slide. It can remove faces while preserving the shell integrity, purify fillets as a special removal case, separate a part from a solid, unite smoothly joined faces with a single face for further modifications, replace face with a spline surface, remove vertices or edges from an open shell. On the right is a group of commands which modify faces. This includes the following: translation of faces by an arbitrary vector, the move command, offset faces by value, rotate faces by an arbitrary axis, and change fillet radius. Here by fillet we mean a chain of smoothly connecting fillets. Now I will illustrate how these functions can be used. So on this slide you can see the illustration of the first feature, which is self-explaining: remove faces. You can see how parts of a solid are deleted. Removed faces are colored in blue here on the slide. This functionality is mainly used to remove holes, the figures on the left, and protruding solid parts, the figures on the right. The operation doesn't build extra faces or edges. It only stitches the existing ones to preserve solid integrity. Here is another example. The different parts of the highlighted feature can be deleted. We show this process step by step from left to right. However, even the whole piece can be selected and deleted, resulting in clear surface. Fillets are special, so their removal and adaptation are separated from the previous operation. We can remove fillets in very different configurations. Generally, it is enough to select only one fillet from the fillet chain, because all smoothly connected fillets are recognized and automatically removed as well. In the center, you can see an example of fillet purification on a sheet solid. On the right, you can see how even some constructive elements can be removed with the combination of remove and purify commands. Sometimes it is necessary to cut off a small protruding part from a large model. It is not convenient to select and remove all other faces, so for this task the create command can be used. The part can be selected and will result in a separate enclosed shell. Now let's consider operations which modify faces. The offset operation allows one to move a face along its normal while preserving the solid topology. All smoothly adjacent fillets are adapted, as you can see on the left figure. The fillet adaptation is used in all modifying operations. On the right, you can see that for cylindrical surfaces, this operation is equivalent to the radius change. This is also valid for spherical, toroidal, and other such surfaces. Here I would like to point out that on the right picture, the change in solid topology is presented. The inner walls orientations are different after the operation. We began developing algorithms for such scenarios where topology may change. I will briefly give some more examples on this regard. Here on the left, you can see the face being pulled outside of the adjacent fillets. They are adapted, but both face and solid topology are changed. On the right, there is just another example of fillet adaptation. Here are more examples of topology change developments. On the left, faces fusion is presented. One of the faces is pulled up to another face and then they are merged together. On the right, there is a disconnection from the touching faces. Bottom plane faces are disconnected from the top cylinder surface. In both cases, topology is changed. However, this functionality is still very limited and works only in certain cases. Now let's consider the similar operation, a move or translation. It is a parallel translation of a face by an arbitrary direction vector. It can be used to move holes or features within one face boundaries. Here you can see how a toroidal hole is moved in the solid. Adjacent fillets are also adapted during this process. For simple faces, this is often equivalent to the offset operation. The next slide demonstrates our new functionality, the rotate faces operation. It was initially developed as a counterpart to the draft operation of a single face. It can be used, for example, to rotate grooves or hinges on circular solids, as shown here. Our fillet adaptation approach allows us to change fillet radius. The algorithm searches all smoothly connected fillets and changes their radii as well. It is convenient because for a long chain of fillets, there is no need to select them all, as you can see on the right picture. They all still will be modified. This operation can be applied even to fillets with variable radius, as shown on the left, but still with some limitations. At the end, I would like to summarize the last year results and our future plans. So, the face rotation feature was developed, the fillet adaptation technique was applied to work with the draft operation. Adaptation of complex fillets, such as fillets by curve and variable radius fillets, is now available. Topology is able to change in some cases now. Also, there are general improvements in certain scenarios, including fillets around seams and poles. New API is developed, including user-defined precision. We will continue to implement topology changes for all face modifying operations. Operation replace a face with another surface is already under development. We will improve adaptation of complex fillets with variable radius. Also, we are working to adapt fillets fused from several parts. We will further integrate the user-controlled precision into our operations. Thank you for your attention. If you have any questions, I will gladly answer them.